The Grumman F11F Tiger was an evolution of the earlier F9F Cougar and represents a significant milestone in the development of naval aviation during the early Cold War. Origins of the Tiger can be traced back as early as 1952, when Grumman began working on a privately funded project to modernize the successful F9F6 Cougar, which was itself the first swept-wing version of the F9F Panther. This new project, internally designated G98, aimed to incorporate advanced aerodynamic techniques to create a more capable fighter for the United States Navy. One of the most notable innovations of the G98 was its use of area ruling in the fuselage design, a concept that reduces drag at transonic speeds by narrowing the fuselage where the wings are thickest. This aerodynamic advancement was complemented by the use of an exceptionally thin wing. The wing of the G98 was a mid-mounted design with a 30-degree sweepback. It featured full-span leading-edge slats and full-length trailing-edge flaps, which improved lift and control at various speeds. In another departure from tradition, the G98 utilized spoilers embedded in the upper wing surface for roll control rather than conventional ailerons. This choice was made to allow for increased flap area for improved slow speed control. The outer sections of the wings were designed to fold downward. Though minimal, this was a necessary feature to conserve space on aircraft carriers. For pitch control, the aircraft was equipped with an all-moving tailplane, which was optimized for supersonic flight, offering better control authority over traditional elevators. To power the new aircraft, Grumman wanted a state-of-the-art, but not untested engine. The design team selected the Curtiss-Wright J65 axial flow turbojet, a license-built version of the British Armstrong Siddeley Sapphire. This engine had already proven its reliability in the North American FJ3 Fury and the Republic F84F Thunderstreak, both of which were in service by the early 1950s. By choosing an engine that was already operational, Grumman hoped to reduce the development time and mitigate the technical risks often associated with new power plants. The Tiger was initially conceived as a day fighter, and to fulfill this role, it was armed with four 20mm Colt Mark 12 cannons mounted around the air intakes. However, drawing on its experience with the F9F family, Grumman recognized that the new aircraft might also be called upon to perform ground attack missions. To accommodate this dual-role capability, the design included four external hardpoints under the wings. These pylons were capable of carrying up to 4,500 pounds of ordnance, including bombs and unguided rockets. The Tiger could also be fitted with four early AIM-9 air-to-air missiles. Additionally, Grumman experimented with 150-gallon area-ruled external fuel tanks to extend the aircraft's range, though these were ultimately discarded due to higher-than-expected drag. In 1953, the Bureau of Aeronautics expressed interest in Grumman's G98 proposal and ordered three prototypes, designated XF9F9. However, as the design evolved, it became clear that the G98 had little in common with its Cougar family. By 1955, the aircraft had been redesignated as the F11F Tiger, reflecting its status as a new and distinct fighter. For simplicity's sake, we will refer to the aircraft as F11F or Tiger from here on out. Before the F11F could take to the skies, Grumman needed a test pilot who was familiar with the J65 engine. In 1954, Corwin Meyer, an experienced Grumman test pilot, was chosen for this role and was sent to Edwards Air Force Base to fly the Republic F84F and then to the Naval Air Test Center at Patuxent River to fly the North American FJ3 Fury. These flights provided Meyer with valuable experience operating the J65 engine, albeit without the afterburner that would later be used in the Tiger. By July 24, 1954, the Tiger had completed its ground tests and was ready for its maiden flight. Unfortunately, weather conditions proved largely uncooperative. Meyer conducted flights in the more familiar F9F Cougar to assess the weather, but eventually decided to wait for clear skies to ensure safety in case of an emergency. Finally, on July 30th, Meyer was ready to fly the Tiger and conducted two back-to-back flights, almost without fault. Remarkably, he achieved supersonic speed in a shallow dive, even without the afterburner. During the second flight, Meyer conducted altitude tests up to 40,000 feet. The flight was going smoothly until he reduced power in preparation for his descent. At this point, the engine started running rough when idle, and Meyer found that it would run more smoothly when at a higher power setting. Meyer also found that deploying the air brakes resulted in severe buffeting of the aircraft. The higher power setting and inability to use the air brakes resulted in a very long descent, raising concerns about running out of fuel before landing. After this flight, the air brakes were fitted with larger hinge gaps to eliminate the buffeting issue. The engine problems were traced back to the blunt contour of the air intakes. Following these modifications, the Tiger underwent 2 weeks of high-speed flight testing, still without the afterburner, before Grumman was ready for a public demonstration, after which the Navy ordered 388 units. In 1954, Grumman submitted the Tiger for its Naval Preliminary Evaluation. In October, Commander Tag Livingston became the first Navy pilot to test the Tiger. During this flight, Livingston experienced the first critical failure of the program. After 20 minutes of flight to familiarize himself with the airframe, Livingston conducted tests not previously done by Grumman. He experienced an engine flameout and was forced to make an emergency landing. Simultaneously, Grumman test pilot Meyer was flying the second Tiger prototype. Knowing Livingston was attempting a power-off landing at an unfamiliar airfield in an unfamiliar aircraft, Meyer advised him not to let the speed drop below 135 knots. Meyer watched as Livingston's aircraft crashed into the pine trees and immediately reported the incident, assuming Livingston had perished in the accident. Luckily, when the rescue team arrived to deal with the situation, they met Livingston stumbling out of the woods in a daze, but with only minor injuries. The aircraft, however, was damaged so severely that it was impossible to determine the cause of the engine failure. The second airframe was later ferried to Edwards Air Force Base for further testing to focus on the engine limitations. These tests aimed to determine why the engine failed to restart during Livingston's accident and to establish the altitudes and airspeeds at which the aircraft could safely restart after a flameout. During these trials, Meyer performed the first intentional engine flameout of the program over the 10-mile diameter lake bed at Edwards as a safety measure. After a few flights, Grumman and the Navy concluded that the Tiger had a satisfactory recovery envelope. While these tests were ongoing, Grumman had the experimental afterburning J-65 engine delivered to Edwards Air Force Base. After fitting the afterburning engine, Meyer climbed to 35,000 feet and accelerated to Mach 1.03, successfully demonstrating the Tiger's ability to go supersonic in level flight. However, while at Mach, Meyer's Tiger experienced a violent explosion in the engine. The chase plane reported a large fireball exiting the engine, but visually the aircraft appeared undamaged. Meyer safely landed the plane, but upon examination, it was discovered that a large hole had been burned through the afterburner shell and part of the fuselage. With the afterburner removed again, Meyer conducted further test flights to explore the aircraft's high-speed envelope. The program proceeded with the following 10 flights going without incident until a test was conducted to push the aircraft's speed to the limit. During this test, Meyer put the Tiger into a dive from 22,000 feet, reaching a speed of Mach 1.1. The plan was to maintain speed while testing flight control stability until reaching an altitude of 7,500 feet, where a 7.5 G pullout was planned. As Meyer neared 7,500 feet, another explosion occurred, and the cockpit filled with mist. Nearly blind, Meyer recovered from the dive, recording a maximum load of 9.2 Gs. The engine began running roughly again, and Meyer limped the aircraft back to base. A post-flight inspection revealed that the emergency hydraulic ram air turbine had deployed itself during the dive and was torn off, disconnecting the hydraulic lines and causing the mist that nearly blinded Meyer. As it was torn away, the turbine damaged the fuselage and dented the horizontal stabilizer. In the air duct, a large portion of the aluminum cover had been torn away, restricting airflow to the engine. 2 3-pound steel uplocks were also ingested by the engine, spinning against the front rotor blades. In Meyer's own words, it was like balls on a rotating roulette machine. Once again, the aircraft was repaired, and the ram air turbine was completely redesigned. The next stage in the flight testing involved spin tests. Early tests went smoothly, demonstrating favorable spin characteristics. After completing the test to the Navy's satisfaction, there was a minor unrelated change made to the rudder in an attempt to solve vibration problems at transonic speeds. The rudder's trailing edge would be increased to 1.5 inches wide, in contrast to its original knife edge profile. The following week, the Navy requested spin tests to be conducted once more, as the rudder changes may have altered the flight characteristics. During spin testing, Grumman's policy was to include an anti-spin chute in the tail in case of an unrecoverable spin. This had been removed after the initial testing, but was almost left off as engineers believed the change in performance to be minimal. However, Meyer insisted on reinstalling the anti-spin chute, a decision that proved crucial. During the first spin with the new rudder at 20,000 feet, the aircraft went completely out of control, oscillating around all three axes. Meyer nearly blacked out but managed to instinctively deploy the chute. At 12,000 feet, now pointing straight down and hanging by the chute, he cut the chute and recovered from the dive. It was later discovered that the new rudder proved almost twice as effective as the original. After restricting the rudder angle to reduce its effectiveness, Meyer conducted further tests, this time from 30,000 feet to allow more recovery time. He encountered difficulties putting the aircraft into a spin, a maneuver that was second nature to him. He then realized he had failed to hook up his oxygen mask and was experiencing anoxia. After addressing the issue, he returned safely and resumed testing the following day. All configurations successfully passed spin tests. By 1956, the Tiger was accepted into service in limited production as the F11F1. Despite the production contract, the Tiger continued its testing phase. On September 21st, Grumman test pilot Tom Attridge conducted gun tests on the F9, F8T, and F11F1. Attridge conducted a series of 6 tests firing the guns in level flight at an altitude between 40 and 50,000 feet. Each test resulted in an afterburner flameout. This was likely due to the position of the guns around the air intake, resulting in the engine ingesting the exhaust gases. Attridge noticed that the afterburner would reignite with ease after each flameout. The next series of tests were conducted with a starting altitude of 20,000 feet and required Attridge to maintain supersonic speed. In order to maintain speed, Attridge put the Tiger into a slight dive, maintaining about 0.8 Gs. The first test in this configuration went without fault, and Attridge landed to refuel and reload the guns before performing another trial. While on the ground, it was noted that there were a few minor scratches on the vertical stabilizer. The cause was unknown at the time, and the crew decided it was not critical enough to delay flight testing. The following flight, Attridge would report that he had emptied the ammo belts while in a dive, before feeling a thud as if he had run into something. The engine immediately began to run rough, requiring Attridge to reduce power until it smoothed out at about 70%. Not knowing what had happened to his aircraft, Attridge flew back to the Grumman Calverton Airport. The return flight would be largely uneventful until Attridge had prepared to land. When deploying the flaps, something embedded in the air intake was dislodged and ingested by the engine. In Attridge's own words, he heard what sounded like a Hoover vacuum cleaner picking up gravel from a rug. Attridge was forced to cut power completely and crash-landed in the trees about half a mile short of the runway. Attridge suffered numerous injuries, including a broken back. However, he made a quick recovery and was flying again within 6 months. After inspecting the crash site, it was discovered that the Tiger had shot itself down during the flight. Attridge was flying a curved trajectory to maintain speed and had managed to intercept his bullets that were slowing down. 4 bullets were discovered to be embedded in the airframe, 1 at the base of the windshield, 1 hit the engine, a 3rd hit the nose cone, and the 4th temporarily embedded itself in the air duct. It was this 4th bullet that had been dislodged during the landing attempt, dealing the killing blow to the engine. While this is without a doubt the most famous occasion of a jet fighter shooting itself down, it would not be the only case, as shortly after a similar incident occurred with an F-100 Super Sabre flying a similar flight profile. Both the Navy and Air Force subsequently agreed that future supersonic gun trials would be conducted in level flight. By April 1956, the Tiger would be ready to undergo carrier suitability trials. Prior to its trials aboard the USS Forrestal, the Tiger would conduct 84 land-based arrested landings with sink rates up to 17.4 feet per second. Once approved for carrier trials, the Tiger would conduct an additional 66 arrested landings, covering on and off center arrestments, as well as 56 launches from hydraulic and steam catapults, with acceleration up to 5.4 Gs. Finally, the Tiger would enter fleet service in March 1957, assigned to Attack Squadron 165. In the same month, the first Vought F-8U-1 Crusaders were delivered to VF-32. The Crusader immediately outclassed the Tiger's performance, ending the Navy's procurement of the Tiger, canceling the initial order of 388 units, and terminating production after only 201 units were built. Near obsolete by the time of its introduction, fleet service of the Tiger would be brief, with the last examples being pulled in 1961. However, due to the good handling and excellent structural characteristics, the Tiger would be used as an advanced trainer in the jet transition training units, a capacity it would fill until 1967. The longest tour of duty was its service with the Blue Angels, where it would serve from 1957 to 1969. An attempt to future-proof the F-11F began in 1955 as a study to fit the new General Electric J79 engine into the F-11F airframe. This engine, the same found on the F-4 Phantom, was significantly more powerful than the J65. This project would be designated G98J by Grumman and F11F1F by the U.S. Navy. The Super Tiger, as it was known, first flew in May 1956, reaching a top speed of Mach 1.44. A few minor modifications would be made to the airframe before further tests were conducted. Later, the Super Tiger would become the first naval aircraft to break Mach 2, significantly outperforming Grumman's expectations. In 1958, the Super Tiger would even set a world altitude record, reaching 76,939 feet. Despite the impressive performance over the Tiger, the Super Tiger was never ordered into production. There was some foreign interest in the project as well. However, all attempts to sell the aircraft outside the U.S. would fall through, with most nations favoring the Lockheed F-104 Starfighter, likely a result of the infamous Lockheed bribery scandals. By 1962, with the implementation of the Tri-Service Aircraft Designation System, the Tiger and Super Tiger would be redesignated F-11 and F-11A respectively. Overall, it was a competent and well-built aircraft. The biggest thing holding it back was the new afterburning engine, which was built by a company with no prior experience with afterburners. Despite its faults, it, along with the F-4D, had pioneered supersonic naval aviation. Though overshadowed by more advanced designs, the Tiger's innovative design features and its role in advancing supersonic naval aviation should not go unnoticed. The lessons learned from the development and operation of the F-11F Tiger provided a valuable foundation for the design of future naval fighters.